Good morning class, today we will discuss the chemical thermodynamics in a pressure cooker. Before I explain any deeper, let's take a look at a video on how a pressure cooker works.
Hello everyone, this is Susie. Today I'm going to show you how thermodynamics works inside this pressure cooker. That's a highly useful tool for us for faster food cooking using heat and pressure. Let's break it down step by step. First, I'm pouring 2 kg of water at 25 degrees Celsius into the cooker. Now I see this cooker and put it on the stove. Since this is a closed and rigid system, no water or steam escape when it's heated, and the volume stays the same. This means the total amount of water stays constant from start to finish. As it heats up, the heat energy flows in from the stove to the water. According to the first law of thermodynamics, the energy cannot be created or destroyed. It only changes form. That's why the heat energy raises the water internal energy. Then after about 15 minutes of cooking, the pressure stabilizes around 45 kilopascal. Steam escapes gently through the bulb, keeping everything safe while cooking your food faster. That's the thermodynamics in action. Heat increases internal energy, pressure rises, boiling point goes up, and then phase changes happen. The safety valve does its job. All this work together to get your meat done quicker.
After viewing the video, how does the first law of thermodynamics apply to a pressure cooker? Anyone? Yes, really.
In delta U equals to Q minus W. Q will be the heat from the stove entering the cooker, raising the internal energy of the water, steam, and food. Change in internal energy will include water temperature rising, steam forming, and the food heating up, all reflecting an increase in internal energy. Finally, the lid is sealed. The volume remains constant, so no work is done. When the steam is released, the system does expansion work on the surroundings, and some internal energy leaves the escaping steam.
Excellent, Huilin. How about the second law of thermodynamics, Sue?
Heat naturally flows from the hot stove to the cooler food. Increasing pressure raises the boiling point of water and allowing the food to cook faster. Entropy inside the cooker increases during heating and steaming, but compared to conventional boiling, the overall entropy generation is lower, making the process more energy efficient.
That's right. So in short, high pressure raises the boiling point, speeds up the cooking, reduces energy losses, and makes the process more efficient. Passing on to Professor Keaton to explain about the calculations involved in the pressure cooker.
Hello, I'm Keaton and I'll be presenting to you my calculations for the pressure cooker for CTD group project. Here are the list of formulas. So in the list of formulas will be the delta in internal energy plus kinetic energy plus potential energy, and then gives you the heat supply plus work done. Then since there is a closed system, the internal energy of delta will equals to total heat supply plus work done, because the kinetic energy and potential energy is zero. And since the pressure cooker is a rigid vessel, the work done will be zero. Thus, the internal energy change will be the same value as total heat supply. For the sensible heating, which is Q1, is the mass times heat capacity times temperature difference between saturated temperature and T1. For the vaporization, which is Q2, it will be the mass of the vaporized water times latent heat. Then W change will be the same as total heat supply, which is Q. Then lastly, the entropy change. For the entropy of the liquid will be the mass times heat capacity times ln of T1 out of T2. Then for the entropy of the vaporized water will be the mass of the steam with vaporized water times latent heat, then is to divide with the saturated temperature. So here are the list of the values that I'm going to be using for the calculations onwards. And now let's look at the calculations. So for the total heat, we need sensible and latent heat plus together. So after I use sensible heat formula, the answer I got was 714.96 kilojoules. Then for the latent heat, I calculated and it gives me 334.35 kilojoules. Then for the total of the heat supply, I plus both of them together and that gives me 1049.31 kilojoules. Then for the enthalpy change, it will be the same as total heat. It will still be 1049.31 kilojoules. Because since the pressure cooker is a rigid vessel, the work done is zero. Thus the Q will also be 1049.31 kilojoules. Then the last part of the calculations will be the entropy change. For the entropy of the liquid, I use the mass times the heat capacity times ln of T1 out of T2. It gives me 2.11 kilojoules per Kelvin in 3 significant figures. For the entropy of the vaporized water, it will be the mass of the vaporized water times latent heat divided by saturated temperature, and it gives me 0.872 kilojoules per Kelvin in 3 significant figures. And lastly, for the total of the entropy change, I plus both of the values together and it gives me 2.98 kilojoules per Kelvin in 3 significant figures.
Interesting. Now I'll open up the floor for any questions that you might have. Anyone? Yes, really.
Cooker cools down naturally after cooking. Does the system pass back through the phase equilibrium line?
Yes, as the cooker cools, the temperature and pressure inside increase. Eventually, the system will move along the phase diagram back toward the saturation curve, and if the water vapor condenses, it will do so at the temperature and pressure corresponding to the equilibrium between liquid and vapor. Any more questions? Yes, Sue?
At high pressure, water boils at a high temperature, right? So how does this shift the phase equilibrium point?
Good question, Sue. So, increasing the pressure raises the boiling point of the water, meaning the liquid-vapor equilibrium occurs at a higher temperature. On a phase diagram, this shifts the phase equilibrium line upward in temperature, so water remains liquid at temperature above 100 degrees Celsius under higher pressure. Will that be all?
Yeah. Yes.
Okay, well, class dismissed.
In 3, 2, 1.
Hello, I am Keaton.
I need to raise my hand.
Q will be the heat from the stove entering the cooker.
Wait.